during this Congress, the activities carried out for over 10 years by our research team on the applications of pulsed electric field to improve the process of winemaking. I just want to tell you that this technology is a procedure, a physical procedure, allowing us to process at lower temperatures than usual, avoiding adverse effects of heat on sensory characteristics. The specific action mechanism can allow us to improve competitivity of wineries, reducing energy costs and also reducing the use of chemical compounds. I've divided my presentation in 3 sections. First section, I will be talking about the fundamentals of this technology, and then I will talk about the 3 main applications in winemaking, which are improvement of phenolic extraction during red winemaking, triggering of yeast autolysis during aging on the lees, and microbial decontamination of musts and wines. What is this PEF processing? It consists of on the application of intermittent pulses of very short duration, just microseconds, of a voltage between 2 electrodes where the product is being placed. Despite the high voltage applied, the short duration of them, around a millionth part of a second, accounts for the low negative impact. When we apply this voltage, electrical field is created, whose strength would depend on the voltage and duration, creating a very curious phenomenon called electroporation, which is the increase of permeability of cells due to the formation of pores in the cytoplasmatic membrane. In order to understand better the importance of this phenomenon, we need to remember that the cell is the way of a life that is the simplest. Many beings are unicellular. In other cases, cells join together in order to create pluricellular beings. In any case, the cell is surrounded by the plasmatic membrane with 2 layers of phospholipids with proteins embedded. The function of this membrane is to protect the cell from external aggressions and to regulate exchange of substances between the inner and outer part of the cell. So we could compare this membrane with the rampart of a medieval city. The stones would be the phospholipids and the gates would be the proteins. What happens when we apply a pulsed electric field? Is it as if we were bombarding the ramparts and we're able to go into the town from different sides, different doors or gates? All the presentations you will be hearing today are based on electroporation of cells. Electroporation of cells in the skin of the grape and also on the cytoplasmatic membrane of the organisms. So let's see the first application, the use of this technique to improve phenolic extraction during red winemaking. Here today we don't need to insist a lot on the importance of polyphenols in the process of winemaking of red wine. They are responsible for their sensory properties, of their capability for aging due to their antioxidant properties, and also they are the reason for their health-promoting properties for the moderate consumption of wine. And these polyphenols are mainly located in the skin and the grape skin. To extract these compounds, there are several challenges, such as reduction of the production capacity of the wineries, because a volume of tanks of fermentation is occupied, around 25% are occupied by grape skins, also costing manpower and energy for periodically pumping the fermenting must over the mass of skins. And finally, it is difficult to control fermentation temperature because there's a mix of compounds, of solid and liquid compounds in these fermentation tanks. We thought that if we were treating the skin with this technology, we would be able to electroporate the cells, enabling the extraction of polyphenols and reduce or avoid some of the inconveniences or drawbacks related to the process, as I mentioned before. This picture here shows one of the first outcomes or results in our lab, comparing color of must containing non-treated grape to PEF-treated grape at different intensities. You can see very clearly how this treatment promotes the extraction of polyphenol compounds, and this extraction is bigger when the treatment is more intense. This effect, after only 1 hour of maceration, was kept over the stage of maceration and fermentation. Here you can see the evolution of intensity, color intensity, content in anthocyanins and total polyphenol content, where we're using the Tempranillo variety. Non-treated grapes are in line black, and line blue and red, where the maceration at 2 different intensities of pulsed electric field treatment. So here you can very clearly see how this treatment increases the extraction of polyphenols, and also to reduce the contact time of skins with the rest of the must that is fermenting without affecting the value of these indexes. These advantages at the end of this maceration and fermentation process were also seen during the later stages. Here you can see again the evolution of these 3 indexes during aging or different stages of winemaking, at the end of maceration, at the end of alcoholic fermentation, and at the end of the malolactic fermentation, and also bottling after 4 months after bottling. So the comparison of the grape, the treated wine is in the red line, and the black one is the control group. So you see the evolution of these indexes over the 3 stages is similar. So the benefits that we could see at the end are also maintained over all the time up until bottling. A similar behavior was also seen in aging in oak barrels and also aging in bottle. When we studied the composition of individual polyphenols of wine treated with this PEF technique, we saw that the treatment does not promote extraction of some specific polyphenols, but in general terms, all polyphenols are extracted in the same proportion. It would have been useless to increase the extraction of these compounds if the treatment impacted the properties, the sensory properties of the wine. In all the wine tastings, expert tasters reported that this treatment had no impact on sensory properties in a negative way. no aroma or flavor, different from the expected, were perceived. So the sensory profile was similar, maybe higher astringency in the case of the grape treated with this PEF technique due to a higher concentration of polyphenol compounds. So this technique enables the extraction of polyphenol compounds and get wines with higher concentration of compounds and reduce the time of contact between grape skins and the must that is fermenting. I would just like to show you very quickly how we escalated this technique. First studies were carried out with a treatment chamber, a static treatment chamber with only 25 kilos of grape, but the amount of wine was not enough to carry out aging studies or sensory properties studies. Then we were able to apply continuum flow system, first of all with around 120 kilos per hour, so we were able to achieve higher volumes of wine in order to carry out the studies on aging, and then winemaking in experimental wineries up until 3 tons per hour. This technique was also validated in a big winery, as you can see here. You can see here the processing of the grape at a flow of 15 tons per hour. The chamber, the treatment chamber, was located at the time of the, or at the point between the stemmer crusher to the pumping. You can see here how the treatment chamber is inside this metal box due to safety reasons. In 2020, this technology was approved by the International Wine Association, and this regulation was transferred to European regulations. So right now, this technique can be used in wineries without any legal obstacle. Now, the second application that I will be talking about is the triggering of yeast autolysis during aging on lees. It is very well known that this stage is key during sparkling wines, but also lately this technique has been in use for the making of white and red wines, because it gives them certain properties. During aging on lees, we will be keeping yeast that were used during the fermentation process in contact with the wine after fermentation is done. And during this time, autolysis of yeast by their own enzymes happens, and the leak of the outcome into the wine. You know that nanoproteins are the main part of these outcome that are mainly located in the cell wall. The problem of this practice is that this process is a very slow process, requiring longer contact times between wine and the yeasts that are going through autolysis. That affects demobilization of stalks, and also labor is needed because these yeasts tend to go to the bottom of the tanks, and that can jeopardize the processes of winemaking. We thought that if we treated yeasts with our PEF technique, we could accelerate autolysis of yeast and accelerate the time of aging on lees. Our hypothesis was that if we electroporated the cytoplasmatic membrane of yeasts, among other things, there would be injection of water, because the membrane is is weaker, and these would produce autolysis of vacuoles, and the autolytic enzymes would be able to go through the membrane through these pores that we created in the cytoplasmatic membrane. Here, in this slide, you will see a comparison between controlled yeasts and yeasts treated with PEF at different times of incubation. You can see here that after the treatment, there are no differences from the morphological point of view between the two groups. We only provoked formation of pores in the structure of the cytoplasmatic membrane that has nanometer dimensions. But after 7 days, we see morphological treatment appearance that shows that the process of autolysis has started. In the case of control yeast, we had to wait for 30 years in order to start to see morphological changes. In order to keep confirming our hypothesis, we had to see how this enzymatic activity was different. As you can see here, the one treated with PEF show higher beta-glucanase and protease activity, which are responsible for the natural autolysis. Here you can see the liberation of nanoproteins after some time of aging on these of a Chardonnay wine. The green line is the control wine with yeast, not controlled yeast, and the red line are wines with PEF-treated yeast at 2 different intensities. The highest extraction of nanoproteins after 6 months in the control wine was achieved after only 1 month in wine with treated yeasts with this technique. These manoproteins freed by treated yeast had properties that were expected in other manoproteins. Here you can see a comparison between control wine and wine after aged after 1 month of aging on lees. You can see how the wine is clearer, and also the wine with PEF-treated yeast show less astringency after only 1 month of aging on lees, and this wine also had capability of creating foam due to the manoprotein activity. So this technique allows us to accelerate yeast autolysis and reduce accordingly the time of aging on lees by winemaking or wineries for certain wines. I will end up my presentation with the microbial decontamination technique of musts. Microorganisms are key in wine creation for the alcoholic and malolactic fermentation, but wine can also be polluted by spoilage microorganisms. In order to avoid spoilage of wine, we need to control both the fermentation microorganisms and the spoilage microorganisms. The techniques that are used are the addition of sulfates and sterilizing filtration before bottling. These both techniques have some problems or drawbacks. They can have allergic impact on certain persons and people, and they also require high cost, and also high pressures that have to be applied can have an impact on quality because the wine needs to go through certain filters. As with other types of cells, yeast and bacteria involved in spoilage of wine have a cytoplasmic membrane regulating the exchange of substances between the inside and outside of the cell. If we electroporate this membrane, there would be different selective permeability that can help kill microorganisms. In this slide, you can see a diagram of this processing for decontamination with pulsed electric fields. First of all, we create this thermal chamber and then a second thermal tank to apply the technique. The time of the product in the treatment chamber is just a second, less than a second. There's always an increase in temperature that is unavoidable. However, this increase for a very short time, because the residence time is very, very short, is also very short because in the second exchanger it gets cooled down. Here you can see on the right side a temperature time profile and comparison. You see how the peak is lower in the PEF treatment and thermal charge, as the area below the curve is much less in our treatment technique. This slide shows you some examples of the efficacy of this efficiency of microbial inactivation, both spoilage microorganisms in both must and wines. I will show you now a study whose purpose was to assess the efficacy of this technique as an alternative to sterilizing filtration. We started with wine that was ready to be bottled, and we compared it with wine treated with 3 different intensities of PEF, and then compared with the sterilizing filtration. After 3 months, we compared enological parameters. We didn't see any differences between the control wine and the PEF-treated wine. The only main difference was a less intensity in color index in the wine that was treated with sterilizing filtration. We carried out triangular sensory assessments, and tasters were not able to differentiate between the 2 wines, PEF and sterilizing filtration. So this technique can be used for decontamination of microorganisms at different stages of winemaking or before bottling. I just wanted to finish my presentation sharing with you some characteristics of this technique in wineries. It can be applied in continuous flows. It is important due to big volumes. Also, installation is quite easy because treatment chambers can be placed in same pipes of the winery, and the space required for this pulsed electric field generator is quite small, particularly if we compare it with similar techniques that are targeted for the same objectives, and the energetic requirements are quite low. In order to electroporate grape skins, we just need 10 and 15 kilojoules per kilogram. That would be equivalent to heating water up to 1 liter of water up to 3 or 4 degrees, and also this technique can offer different applications, so the same generator could be used for different purposes if we connect it to the different areas in the winery, whether it is to extract polyphenol compounds or electroporation of yeast to accelerate their autolysis, or for microbial decontamination. As a conclusion, I would say that it is a technique that could increase productivity in wineries, facilitating rotation of fermentation deposits with savings in energy, also in labor, particularly for the batonnage, and pumping the wine over the mass of skins, and also reduce the use of chemicals and saving investment in sterilizing filtration steps. I just wanted to end acknowledging the support of the wineries and institutions that have supported us, and also the people participating in our team that have participated in all these studies. Thank you for your attention.
Yeah, thank you very much. I'll speak in English as my Spanish is not very good, or almost not existing. I'm Stefan Toepfl, Managing Director of the company ELEA, which is a manufacturer of pulsed electric field systems. And I'm happy to add a little bit from an industrial perspective on what we've just heard from Javier. When we decided to do this as a tandem, I was very happy that we had the opportunity to talk here and to work together on that talk, because pulsed electric fields is something we jointly work on since more than 20 years already, and I wanted to put that also a little bit in perspective. Where is it used in industry, and what do we think in wine will be the benefits, and what equipment is required? ELEA was funded in 2012 as a company dedicated for marketing pulsed electric field systems. And at this time, we thought more the use of the technology will go into wine processing and juice processing because of the effects Javier has just described: extracting, improvement, mashing, and increasing polyphenol yields and so on. But by a number of coincidences, we came to a completely different application at the time in the potato industry. Why am I mentioning that? Because I think it's important to know in the potato industry, within 10 years, PEF, or pulsed electric field, has turned into the standard technology, around 300 machines installed, and you will not find any French fries or potato chips on the market anymore which have not been treated by the technology. And this application has helped to take the use of pulsed electric fields from a lab scale curiosity into an industrial practice. What is important with the relevance to wine is potato is a very low-cost crop, 24/7 operation, high reliability, high robustness required, and what I'm trying to say here is the equipment is available because of that. For potatoes, also just to give you a number, typical standard size machine is 60 to 100 tons per hour, so we're also not talking about the technology which is existing in a lab scale only or in a technical scale. It's full-scale industrial systems, hundreds of those around, also in Spain or Italy. Not so much in French fries processing, because Spain and Italy are not so active in that field, but potato chips, a lot of machines run in Spain and Italy as well. So coming back to wine, where do we see the benefits? Actually, exactly where Javier was just telling. We see 3 application points in the wine industry: very early stage on the mash, a second opportunity on the lees, and a third one when treating the wine. The benefits have just been mentioned, so I will not have to talk about the benefits of those 3 stages anymore. Important is the same machine can be used at all 3 stages of processing. So if you have a pulsed electric field systems, you can use it for the mash treatment, you can use it for the lees treatment, and you can also use it for decontamination of the wine. With one thing to be kept in mind: the treatment scale or the throughput is different. Javier mentioned it already. Different energy input for different application, and different energy input means a certain machine with a certain energy output can treat a different throughput at a different stage. When we talk about mash treatment, that is the lowest energy input requirement, so the throughput is almost the highest, which fits very well into an industrial wine processing, because when you're processing the mash, you would want to have a high throughput because it needs to go fast. The grapes are coming in, you want to get them into the fermenting or in the mash tank without any delay. The process here is, that's a smaller scale system shown on the picture. pulse generator, a treatment chamber, you pump through the treatment chamber. The treatment chamber on industrial systems typically has 80 millimeter or 100 millimeter pipe diameter. This is where we treat, and we treat the material in a pipe in a continuous flow. That has been shown already. Idea is increase color yield, polyphenol yield, anthocyanin yield, and yield in general. When we talk about the lees treatment, the throughput is a little bit lower, but that also fits into the industrial winery very well because you don't have the same amount of lees to be processed than you would have grapes. So actually the throughput need at this stage at operation is much, much smaller. Anyway, we have done own work also, not so much in the wine industry, but PEF is now also used a lot in spent brewers yeast applications where yeast autolysis is needed. So you take the yeast from the brewery, you treat it, the yeast is autolyzing itself, and you can use it for producing amino acids and flavor extracts out of the yeast. So the wine application on lees is actually pretty similar to what is already done in those markets. Wine treatment, decontamination. Most of the machines which are used for decontamination, most of the PEF systems which are used for decontamination are in the fruit juice industry. Fruit juice, orange juice processing, very similar task than in wine. You would like to extend the shelf life of a freshly squeezed orange juice without changing its taste, without changing or adding any chemicals. Pulsed electric fields is in industrial scale use, around 15 machines in Europe running for this application, and it's a very low energy, high volume, low cost application competing to HPP, which would be an alternative process for that use here. So we have those three applications. We have systems doing for that. A few words on what such systems need or how they are put together, or what they are. Oh, just was too fast. What those systems are designed after. They usually consist of a power delivery system. That is the box we see on the top left, which is taking power from the net, 400 volts or 230 volts or 480 volts AC, alternating current, and is converting them into high voltage pulses. We're using pulses because the effect of electroporation only requires pulses, very short, concentrated form of energy, actually very low amounts of energy. I'll come back to that a bit later. Then you need a treatment device. This can be a pipe, like on the picture on the right, where, for example, grapes are pumped through in a mesh form, or those can be belts. Potatoes or other material we would treat on belts. The reason being, we want to process them before they are cut, so the whole material has to be processed. The benefit of a belt is you can process in a large scale, no pump needed, pretty easy system. The disadvantage is those belts are comparably big. A pipe system is a much smaller setup, and pumpable material like grapes, I would go through a pipe system here because it's easier to integrate. For grapes, actually both is possible, but reasonably speaking, we would look into applying pipes here. Power delivery, treatment device, those are the two components. You need, from a parameter perspective, a certain field strength. Those levels have been mentioned before. We talk about kilovolts per centimeters. Why do I stress that? The kilovolts cannot become too high. Typical industrial systems allow up to 30 kilovolts of voltage to be used. If you're going much higher than 30 kilovolts, you will have difficulties with safety, with labeling, with operators, training, and so on. So if we need 1 kilovolt per centimeter and we have 30 kilovolts, that means that the electrodes can be 30 centimeters apart from each other. That's why I'm mentioning that there's a size limitation because of that field strength need. So when I said before, the pipe diameters are typically 80 millimeter, 100 millimeters. That is a result of the field strength need, but grapes can be perfectly pumped through that setup. Energy levels, Javier already mentioned those numbers, approximately 10 kilojoules for grape treatment, 15 kilojoules for lees treatment, and 80 or 100 kilojoules per kilogram for wine. If you can't work with those numbers, or if you don't know how to translate them, I added in brackets here the numbers per 1,000 kilogram and kilowatt hours. So 10 kilojoules per kilogram corresponds to 3 kilowatt hours per 1,000 kilograms, or if you calculate with 10 cents electric energy costs per kilowatt hour, which would be a pretty standard industrial price value, we talk about 30 euro cents per 1,000 kilograms of grapes to be processed. So in comparison to the energy you require for cooling in the winery and for many other things, the electric energy costs are actually neglectable. Here we talk about very, very low energy requirement because the energy into those forms of pulses. That's a little bit different if we talk about microbial inactivation. We require higher energy inputs here. Here it's 30 kilowatt hours per 1,000 kilograms, or 3 euros per 1,000 liters of wine, or 0.3 euro cents per 1 liter of wine. So also not high numbers, but higher than for the grapes treatment. Yeah, last but not least, equipment needs to be safe, easy to integrate, robust. But actually that question is solved. As mentioned, we have 300 machines in potato processing industry running day in, day out. Keys, metal, robust design. The metal helps preventing excess, keeping it closed, preventing any electromagnetic interference and so on. As long as the machine is closed, it's not dangerous. Despite you might think high voltage and water is difficult to combine, actually safety-wise, you can keep that very well under control. Size-wise, we have 3 different ranges, or actually 4. 2 of them are in the same cabinet of machines, which are standardized and also used in other industry sectors, which means wine users share the same platform of spare parts, the same short delivery times, the same servicing needs. That's why we did that. For the larger installations, the P1000 is available. That does up to 48 tons per hour when we talk about extraction improvement. So that suits also pretty large winery setups. You can process grapes with 48 tons per hour and put it into a fermentation tank or maceration tank. If more is needed, you can combine single modules for 100 tons per hour, for example. The P10 and P100 are smaller, 20 tons per hour for extraction improvement, and the smallest system available for industrial use is 7 ton per hour. We've just added a new model. All of them are separate pulse generator and treatment chamber. So you have some flexibility to add the treatment chamber into the line and put the pulse generator 20 meters away, cable in between, and then that would allow an easy integration. We've just added to the portfolio a new design, which is all integrated. We've actually designed that for the olive oil business, but to us, olive oil and wine are somewhat similar because often the throughput ranges are similar, the geographic ranges are similar, they just have different seasons. That is a design where the treatment chamber is integrated into the generator cabinet, which has the benefit of being smaller in the footprint, easier to install, but that model is for extraction purpose only. So other than the other systems which did allow inactivation and extraction use, that particular model is designed for up to 8 ton per hour of extraction improvement in a small size. That's 1.20 meter times 1.50 meter, just to give you an idea. So basically the size of a Euro pellet is what you have to imagine as size of the equipment. Yeah, to sum up here, the technique is proven, commercially viable in fruit and vegetable processing, so crops with much lower value than wine. Wine, we still always have to talk about seasonality of the production and how do you handle that. The technique is very low energy and heat requirements. It's driven by investment, not by the energy requirements. A lot of lab scale and technical scale work is around. We've actually done a lot of research, books, papers since 20-25 years. So we are sometimes wondering ourselves why in the wine industry we have not been so successful yet. I think part of it has been the lack of availability of larger scale machines. And that's why I took the detour through the potato industry. Potato applications have helped to make that available. And last but not least, as already mentioned, the treatment is approved by the OIV, is also added into the European wine guidelines, 2019-934, it's listed on the positive list. Treatment of grapes is something which can be done and which is allowed. So, yeah, summarizing, I would say it's exactly the right time to get started with applications in wine because all the preconditions, all the prerequisites are available and at hand.